So, so good morning or good evening, everyone, based on where you are. Yeah, we have great pleasure of first having Origin of Life session in this ARN seminar. And our first speaker is Professor Doron Lancet from the Weizmann Institute of Science. And he's going to talk to us about some work that he's been doing for almost 2 decades now, and maybe even more.
Actually, three.
Three, yes.
Yes, it is
Exactly. And
more.
and we're very happy to hear all about it and where it's come and yeah, so please take it away.
Okay. So, shall I start?
Yeah.
Okay. So, what is clear is that I am coming with ARN here and not RNA. Okay. It's interesting because these are the two different ways of looking at origin of life. People begin with RNA or they do something else, and that else is networks. Okay. So, basically, I say almost everything is wrong for me in the literature of origin of life. So, for example, people think that you have to make first all the molecules that you need for life, and then something will happen, they don't know what. And what we say is that there are already all the molecules from meteorites, from everything else, and if some electricity that do make some of those molecules, no problem. But we don't have to worry about this because there is a very large number of molecules, and there is a lot of reference for that. Okay, so there is this, and then there is a brown primordial organic soup, and then there is what I'm going to tell you about, and this should go to life. So that's quite different from a lot of other things that people show. So RNA and lipids, there are two different worlds. We think RNA world is wrong in so many ways that I don't have time even for a whole hour to explain. And lipids are much better in that respect. What happens when you reproduce? Because as you know, NASA says very clearly, you have to reproduce. Something has to reproduce. The idea that RNA can reproduce without any networks, that doesn't work, despite a lot of efforts. And then there is, it is actually reproducing the sequence. That's very complicated. And on the other hand, there is something called compositional information passing from one generation to another. And this is actually much easier to do, but you have to find out how to do that. Now, compositional reproduction is central in today's living cells in all cases of epigenetics. And you can see all of those. Most people know about it on the right side, and we heard it last time. But actually, how many copies of each transcript or protein or metabolome or metabolite, sorry, this is also epigenetic. And of course, also chromatin metabolism with all its complexity. It's really, really wonderful story, but it is in a very, very advance in life. Oops. Now, this I want to say, central dogma says it starts from DNA, then RNA, then protein, then metabolites, and everything else, and including lipids and so on. But we say that life began the opposite way. That is, as you can see here, you have something that begins here. This is a protocell, and then it goes gradually to proteins, RNA, and DNA. Proteins don't need to have necessarily a ribosome. You can have add up to maybe 10 long that is done by other ways. So you can start proteins without DNA, RNA, and towards protein. Self-reproduction of a protocell. What happens? How can it happen? What is clear is that if you have a small one and you have to get a new one with the same composition, this is homeostatic growth, and this is importantly, really, really important. On the other hand, when you split, and if it's fluid and it's random, that's physics, and most of the time, okay, this is almost not important. So what is really important is find a way, a model that will show self-reproduction that is done by homeostatic growth. I want to go a little bit to some details here. Our model does all sorts of things, but clearly what we start with is non-covalent and covalent reactions. It can be in a micelles, I will show soon, and also for vesicles, it doesn't matter. And there can be something in the, for example, in the membrane, there can be a catalyst, organocatalyst, and it can bring in, this is here, this is the non-covalent, and the covalent is that the blue, maybe another blue, what does is put this together with this tail, and it makes that. Okay, so this is generate or synthesis of molecules in catalytic way in the membrane, and it's also good for myself. Next, by these kinds of games, I don't want to go into much detail, but you can actually fill this in a very specific way, metabolic kind, by something like this comes in covalent, this flips, and then opposite reaction, and you load the lumen. And this can be something extremely important if you can do that. Okay. Now, I want to say a few words about my friend, very good friend, Kaufman, Stuart Kaufman. He was really important, and this was very long time ago, actually more than three decades. And what he drew is what you see here, and I know that you all know about it. I know from what we discussed 2 weeks ago. But the point is that this alone cannot work. He calls it catalytic closure, and this means each member has at least one catalyst affording the member's formation. This is sufficient, but not, it's necessary, but not sufficient. And all of these points are in our model that we added to Kaufman. Let me say a few words about them. So containment, he has no containment. So there is no individual, oh my God, I hate this, it just moved by itself. Individuality is extremely important. You cannot get evolution without that, Darwinian evolution. So it really is important. And of course, if you have a membrane shell or something like that, a containment, you have much better ideas. For example, you can define concentrations. He has no concentrations, only names. Graded value of catalytic power, no, he has only yes or no. We are graded. Use thermodynamic facts for catalytic distribution. How much of each kind of value in a network can be, what is the distribution? And I don't want to go even one more about it more, but it has to do with a distribution that should be log normal. I will not say no more right now. And then continued growth to split and allows self-reproduction, that's what I said already, and membrane lumen synchrony in a unified network. So what is that? This means, this is the arrow here, that both what is here and here should be the same in the same network. Otherwise, it will not work. Okay, to start with something very, very small and very simple, we decided to work on micelles for quite a few years. And we have many papers about this. Let me just say that it is a very small assembly, a nano size, okay? But it can do a lot of interesting chemistries. And this is like some advantages. I will go very, very quickly. It's promiscuously and spontaneously done quite easily. Even for vesicles, you have some Some molecules, lipid molecules do it, some don't. For Micelles, most of the molecules can do it, but let's not say more than that. Surface to volume ratio, that's very important. Then there is enhanced concentration. It's like 1 molar can be there. And then diffusion, so it's liquid. And that's very nice, so molecules move from one place to another. This is also, by the way, in membrane. But this is a good model. And then a polarity gradient, that's extremely nice. And also for catalytic effects. And it's also what happens in a protein, as you see at the bottom. This is also out polar, inside hydrophobic. And there are also like mineral, many people use life beginning with minerals. I think that's wrong, but it can be happening for making some molecules, but that's not really going to be life. Okay, so I'll just say there are many dozens and many hundreds papers on Micelles that are catalytic. I will not say much more than that. Then look at that. This is a nucleotide that can become a head. Or here, this does peptides, and so on and so forth. It can do a lot of interesting things. And there is also some information on homeostatic growth from my friend, Stephen Fletcher from Oxford. And there are 3 different kinds of tails. So there are 3 different kinds, or all of them same head, but there are 3 different kinds. And they show that there is this plateau with ratios in a reaction in which I don't want to say any details more, but the idea is that in certain period of time, they are the same, despite the fact that more and more micelles are formed in the reaction. So, quantitative and rigorous chemistry model for support future experiments. Homeostatic growth, I don't do anything, it just moves by itself. Homeostatic growth is the crux of the model, as already mentioned. Okay, this is a set of equations in our graded autocatalysis replication domain. I want to say that I'm a little bit unhappy about saying just that the model is autocatalytic, because then it can be something else than we think it is. But let me just say that we use that name and GARD, and the idea is that it's not really autocatalytic, but it is it's an entity that can make copies of itself. If people say this is the same as autocatalysis, no problem for me. I'm very happy about that. So what happens? We have here in and out, and there is a net, okay, by these 2 reactions, and this is a matrix of catalytics. So if there are 100 different kinds of colors, of course, types of molecules, lipids, amphiphiles, I should say, then we have 10,000 numbers here. Okay, and so it comes here to that, and this is just very simple kinetics. And let me just jump here and say that beta is very simple, but it can be more than 1. For example, if this is entrant, and this is catalytic, there can be multiples. We will see it immediately. Okay, so it's not 1-to-1, it's many-to-many. Okay, let me say a few words here that are important for this model. Both covalent and non-covalent and covalent reactions, all molecules can both react and catalyze, including food. This is for the idea of A and B as food in Kaufman and others after him. So for me, there is no food. There is just molecules all around, and they play the games. Concentrations, they are any number about 0, and the same is, of course, it cannot be very too big, but never mind. And then catalysis power has values above 0, as opposed to just yes or no. And then reaction many to many, I already said that, and cyclicity is unnecessary for production. This is already a result of us, but I want to mention that. Some people think that you need a cycle. You don't. I will, if we have time, I'll speak about it later. Okay, so let's go here. Just to say that for getting what we call the composome, this is moving in the volume of compositions. This is actually a composition is a vector, so there is a direction, okay, and we have to have homeostatic growth. You can only get if you get net flux in vector, same direction as composition vector. That's very simple, but it's nice to say that. Now, how do we see if a composome is there? The answer is that this is we take both times the same axis here and here, and so here is like 40 and 60, and all of this square is a situation in which, because it's red and there are many points here, this means that on many growth and splits, it almost doesn't change its composition. And this is reproduction. Now, very nice and important, we found, people always ask us, how often do you get composomes? And we have some numbers on that, something like 10 to the minus 12 if you make a lot of micelles completely randomly, okay? But there are two things. One is that on an Earth, you can get so big number of micelles that everyone will be, we computed all of that. So you can easily think that it can happen. Some of them will be reproducing. But on the other hand, you can start at different compositions, okay, and wait and see what happens. And this is what happens here. You start here, and this is not composome, and it goes on, and every time there is a shift of the composition, okay? But there is a point in time after maybe a few dozen growth splits that it gets there. That's a very short path, okay? So you can feel that it is possible to either by making a lot of micelles, which is very natural on a huge planet, and on the other hand, by a more like that. And what we know about that, this means that composome is a dynamic attractor. This is, I think, extremely important. I want to say one more thing. When I don't know how many are doing that, but for Kaufman, what he says that that you have to grow. You make more bigger and bigger peptides in that case, okay? And people don't like that. But in our model, something completely different happens. This is the random, just at the first, making the first micelle in a soup. And then when you go this way to a composome, it has only a quarter of the number of molecules, types. And that's very important. So you actually build itself a way by which a network becomes reproduction just by this process. And that's really nice. Okay, let me skip that because I don't have too much time. So, okay, let me continue here. Well, I just say that as I already mentioned, that it can be metabolic, that is, can be with or with the, that it can be covalent and non-covalent. So if it's covalent, it's actually also non-covalent is metabolic. It's like transporting. But anyway, you can do all sorts of things. It's a different one. It's not beta, it's gamma, and I don't want to go too much to that. And that I already told you about, that you can do that loading of the lumen. Okay. Now, very interesting. We tried that also for oligo molecules. Okay, in this case in dimers. So it's like here. You see this plus this. This can be a catalyst. Can be also just one unit here or two, and then this is the result. Okay, so we find that also here we get composomes, and some of them are rich. It's by how strong is the number, the color, or less so. So this is very interesting. And also, when you get to homochirality, something that every people say, first make it homochiral, then there will be life. I say in a very strong way, homochirality comes before by life. So if you have a very simple like thing like we get here that reproduces and is lively, then it does the same. And here you see this is a region of time, and the region of time, this is pure, almost pure D. This is racemic, this is blue, and all sorts of other ways. So these are different molecules here, and you see this is on blue, and this is on red almost, and so on and so forth. It's really, really interesting. So our model solves one more. Okay, let me skip here.
So,
this is
Doron,
also
quick question. Can you say a bit more about what these these matrix plots exactly are? These time by time versus time plots that
same exactly what I showed before, and I'll tell you why. Because the reactions have, let's say, monomers and dimers, just as an example. This is a reaction. It's just like the reaction of getting into the micelle or into the membrane, and so on and so forth. So basically, it's the same. It's the same as I showed before.
Yeah, no. So I'm also confused about the previous one. So yeah, how are they generated?
Can we do it on the discussion? I want to do it if you
Okay.
don't mind. What is the question? Tell me, please.
Yeah.
What is the
Just
exact
what
sample?
are the colors, and how should I read off? Yeah.
The colors are types of molecules. Oh, you mean the red and blue? So on.
Yeah. All the colors on
Oh,
these.
that's easy. It says,
Mhm.
yeah, this is racemic, this is D, and this is L. That's just it.
Right. So but in the previous ones, when they were like, in not this plot, but if you go, yeah, for example, this one. Yeah, the one that you had
This
right
is
here.
this is this is the
Yeah.
colors here is just how similar from T to T1 plus one. Okay, on the watch.
I see. Yeah, thank you.
Okay, sorry about that. Yes, it's different languages here. And this is, I will not get into details, but it's an experiment that was done in more than 10 years ago. And it shows that you start with this small and you go to big and the ratios stays the same. So that's very, very important. Okay, so let me continue here. I'm almost done. NASA. Let me read. Well, we all know, right? Reproducing, sustaining, Darwinian evolution. But Darwinian evolution is the result of reproduction. So you have to go here. Another view is if heterogeneous micelles it can be micelles or any vesicles or anything like that, but it can be anything, but let's forget about that. Micelles can self-reproduce and show compositional mutations, which is very clear happening because there is noise, and then the offspring generate species. It's not rabbits, it's just micelles, but it is species, and hence natural selection leading to Darwinian evolution. I don't care to define what life is because we already have it, but what is clear is that something very simple as a micelle can show a Darwinian evolution. So this is our model, and I just want to say something here that this already begins to have metabolic. So this is a peptide, and this is an oligonucleotide, and you can enrich here inside, and you have to make vesicles. Vesicles can happen just themselves, but they can also be by fusion of that and this and also, and so on, and also change of the, in this particular case, as we know that to make a membrane, it's better, for example, to have more 2 chains than 1 chain. Okay, so if you make some chemical reactions, it will go from here to there. Okay, and this is something that I really admire, and this is Cornish Bowden and Cardianas, and I like the idea that people say, look, all the same, but there is a lot of things beforehand. So there is, of course, there is evolution, Darwinian evolution before Luca. But some other people say, well, but what, without DNA you cannot do? Well, most of the people think that you need the DNA for that, and that's wrong. So the idea is that this should be simple and more, and then, so we put these together, whoops, okay, and you have this, and then it goes to that, and it goes to Luca, and the idea is that if you look at here, this RNA should be very well down the story before Luca, and this is not where RNA can be. So this I already telling you in the beginning, and here this is just the last one. It's a few more details. So I have 2 minutes or 1.5. So this is the molecules. This can go also from here to there, but it doesn't matter. So we go this way, and then you can get, for example, transporters. Transporters, for example, there are papers that show that a very small peptide in a vesicle brings certain molecules in. So this can happen very easily, and then you can have some covalent stories inside here with all sorts of things that I don't show here because it's too small. And this goes polymerase, and then it becomes all the way to RNA. And then this probably didn't happen by itself, because RNA, if you make it, if there is no ribosome, you cannot do anything. Messenger RNA, I mean. So it really has to be a very complex path. And by the end of the day, only after 500 or 400 million years from where we cooled down the second time, you will get Luca. That's it. These are some people that I want to show. There are people that were with me, except Roy, that is now he's listening. He's the only one part. I'm very old, so not too old. So I only have one person working with me, and the other ones are 2 professors and 1 postdoc, and there are many more. Okay, so that's it. Thank you.